Good morning, everyone. This is Yositaka. I'm the director of Yoshitaka Next Bangkok. Today I will act as a moderator of this event. Before starting, I will give you some notices. Okay, so about Q&A. The Q&A will follow each section, each presentation. For online participants, please write your question in Q&A on the Zoom toolbar. Be aware that it may not be possible to answer all questions due to time constraint. And today's video, this event will be recorded and will be uploaded later on NSTDA and Prof website. About the questionnaire to make this event better in the future, please fill out the questionnaire. The QR code is shown in the document as well. And it will be sent to all online participants by email after this event. This event is organized by Yoshitaka Next Bangkok, co-sponsored by Yoshitaka and NSTDA, and supported by Yoshitaka Alumni Association, Thailand. If you have any inquiries, please contact the following email address. This is today's program. Okay, the first opening remarks from Professor Nobuhiro Hayashi, the Yoshitaka Vice President. Please.
Okay, so thank you for my introduction, Tsukushi-san. And dear participants of Tokyo Tech Research Showcase 2023. So I'm Hayashi, Vice President for International Affairs of Tokyo. So thank you for taking time to participate in the hybrid event. So not only at the venue, but online as well. I'm so happy, and by 2024, Tokyo Tech will be merged with Tokyo Medical and Dental Universities, and the two will be formed as Institute of Science Tokyo. Okay, so the name is the Institute of Science Tokyo. And with this integration, we will aim for even greater heads in convergent science. So convergent science is a key word for the future for us. Today's theme, medical devices, is also a topic in advance of this trend. In Japan, the aging population is a serious problem, and the burden on medical care is gradually increasing. In addition, the situation becomes even more serious when we encounter unexpected situations such as this COVID-19 pandemic, unfortunately. In the near future, Thailand is expected to face a similar aging population problem. To solve these unprecedented problems, new science must be created. This requires global communication between science and society. I believe that today's topic, medical sanitary devices, is one such pressing issue for both countries that need to be addressed urgently. In 2018, Tokyo established Next Bangkok in the Thailand Science Park and has since been promoting research and development in Thailand. This event is held every year for the purpose of interacting with Thai researchers and industries and media in the fifth time. Fortunately, the situation with the COVID-19 has a crackdown and it has become possible to hold face-to-face meeting again. So I'm so happy to see you. We hope that all of you who come to the venue will benefit from learning about the excellent technologies of Tokyo Tech and lastly, and enjoy interacting with researchers come here. If you are participating online, so please contact Tokyo Connect Bank and we will connect you with the appropriate researchers. Let's connect this event to our research meaningful to both countries, Japan and Thailand. I hope to see in the near future that the new science created by the collaboration between the two countries will make the world a better place. Last but not least, so I'd like to thank NSTDA for co-sponsoring this event. And the Tokyo Tech Alumni Associations for their great support. Thank you very much.
Thank you very much. Thank you very much. Okay, the next opening remarks from Dr. Sarun Sumriddetchkajorn, NSTDA Executive Vice President, please.
Good morning, everyone. Thank you very much for joining us for the 2023 Tokyo Tech and NSTDA on NSTDA Research Showcase. I think our collaboration between Tokyo Tech and this program, as I talked to Kun Suttisa, we are now about 16 years old. I think it's a very strong collaboration and strong program. NSTDA and Tokyo Tech established the Human Resources Development Program through the International Graduate Program called Thailand Advanced Institutes of Science and Technology, or Thai Tokyo Tech Program, in order to implement the joint graduate programs with Thai University, namely KMUGT, KMITL, KU, FIIT, and MU. This year, specifically, the National Research Council of Thailand, or NRCT, has provided support to our program and shall be a very strong partner to support the program to achieve our goal. In addition, Tokyo Tech and NSTDA foresee that research and innovation are very important for lifting up the capability of industry. So Tokyo Tech and NEXT aim to be the bridge between NSTDA as the National Research Center in Thailand, Tokyo Tech as the academia and research institute in Japan, in order to contribute to the industry in Thailand, Japan, and neighbor countries. The Tokyo Tech and NSTDA Research Showcase is one of the activities which Tokyo Tech and NSTDA would like to introduce the cutting-edge technology to reinforce the capability of industry. Today, the topic of the research showcase is the medical device. For Thailand, there is the 13th National Economic and Social Development Plan, which is targeted for the implementation during the year 2023 to the year 2027. This plan stated one of the very critical targets under the national strategy that Thailand to be the center for high-value medical health. So this aligns with the today talk. I truly hope that all of you will gain a lot of knowledge and see the opportunity from today's showcase and be able to apply for whether your own business or your organization. So last but not least, I would like to express our deepest gratitude to our counterpart Tokyo Tech for today's showcase. And NSTDA and I sincerely hope each of you stay safe and healthy. Thank you very much.
Thank you very much. Okay, then I'd like to welcome the first speaker, Associate Professor Akitoshi Okino. He belongs to Laboratory for Future Interdisciplinary Research of Science and Technology. And today's title is Development of Brand New Atmospheric Low Temperature Plasmas and its Application in Materials and Physical Fields.
Okay, thank you, Chairman. My name is Okino from Tokyo Tech. I'd like to talk about our atmospheric low temperature plasma today. Plasma is the fourth state of the matter. In the case of water, below 0 degree, it is ice and it is solid. And between 0 degree to 100 degree, it is water and it is rigid phase. And between over 100 degree, it is turned to water vapor, and that is gas phase. And if we apply more high temperature, and part of the water vapor is turned to ionized gas, it is plasma. And plasma has chemical reactivity and emissivity and electric conductivity and high temperature. So plasma is used for semiconductor processing or something. In industrial use, plasma generation method is chosen according to demand of plasma pressure and temperature and purity and kind of gas. We can choose discharge frequency from DC to kilohertz, megahertz, or gigahertz, or high voltage pulse. And we can choose discharge type, electrode discharge, barrier discharge, coronal discharge, inductive discharge. And we can choose the pressure from vacuum, low pressure, atmospheric pressure, and high pressure. In usual plasma devices, low temperature, low pressure is used because in low pressure, plasma generation is very easy. But in our laboratory, we are studying atmospheric plasma because it is very special. Atmospheric plasma has some merits. Number one is the plasma does not use a vacuum chamber for pumping system. So it is very low cost. And second one is eliminate pumping. So not batch process, but continuous process can be achieved by atmospheric plasma. And high density plasma can be generated in atmospheric. So high speed processing or high speed processing can be achieved. And the fourth is applicable for large targets, such as car or airplane, and that cannot introduce to a low pressure chamber, but we can grow atmospheric plasma. And there are some difficulties. Generation of atmospheric plasma was not so easy. In the last century, atmospheric plasma were same with high temperature plasma. So they have been used for material melting and decomposition or atomizing. I have been used it in the field of analytical chemistry from my student days about 30 years ago. However, atmospheric plasma has not received much attention in many areas of plasma engineering. In IEEE Plasma Conference until 2005, a percentage of presentation on atmospheric plasma was less than 1%. However, since 2006, percentage has increased dramatically. It was because low temperature plasma became available. This is the video of low temperature plasma. We can irradiate two metals like this, and we can touch the plasma. It is not hot, and we don't feel electric shock. In the low temperature plasma, there are ions, excited species, radicals, and electrons. They have high temperature or high energy. But almost all, over 99.9% particles are still ordinary molecular, and they are almost room temperature. So we can touch the plasma. This is the low temperature plasma, inside of low temperature plasma. I told you about the merit of atmospheric plasma. Now we get a new merit. It is low temperature. So it is applicable for heat-sensitive materials, such as human skin and living tissue, plants, food, and so on. So low temperature plasma is suitable for biological or medical applications. So in recent years, atmospheric low temperature plasma are used for surface treatment and high strength bonding, decomposition, gas decomposition, hemostasis, high sensitive analysis, and disinfection, and agriculture. Our specialty is making brand new low temperature plasma devices. In our laboratory, we made an atmospheric multi-gas plasma jet mainly for surface treatment. In this plasma source, discharge is generated in the body. So just after grow plasma with reactive species is blown out from a small hole here. And so just this plasma source can be generated helium, argon, oxygen, nitrogen, neon, carbon dioxide, air plasma. As you can see from the color of the plasma, each gas produces a plasma with different characteristics. Therefore, the appropriate gas composition must be selected for each application. The plasma gas temperature is around room temperature, so we can irradiate the plasma to paper, plastic, glass, semiconductor, and pipe inside, and vegetables and fruits, sashimi, egg, and that is low temperature, so not damage for stocking. But it is about 320 Kelvin, So ice cream, ice, chocolate were little melted. If we irradiate the plasma source to surface, we can easily hydrophilize almost all materials, such as rubber, acrylic resin, glass, semiconductor, copper, polyimide film. And this is the result of surface hydrophilization of polyimide film. The surface is easily hydrophilized by plasma irradiation. The treatment type is less than 1 second, and the speed was dependent on the plasma gas species. This is the main principle of hydrophilization. And contamination on the surface are removed by reactive species. Then the surface is cleaned up and hydrophilized. Of course, some functional groups may be added to the surface. We developed a new linear type plasma source to process flat surface uniformly and at high speed. This is a video of hydrophilization by our linear type plasma. We can touch the plasma, and plasma is brought out from the slit. In this case, we use oxygen mixed argon plasma. And this is copper plate, maybe just hydrophobic. And we irradiate the plasma in very short time, like this. Then the surface of the copper plate is hydrophilized like this. And this is a sashimi. We can irradiate plasma. Then the surface is hydrophilized, very good for soy sauce. And we can eat it. If we use hydrogen mixed plasma, hydrogen radicals reduce the copper surface. So the copper oxide can be removed in short time. In this case, we use a 3% hydrogen mixed argon plasma. The plasma can be reduced copper here. This line is removed copper dioxide. And this is the plasma jet source for surface coating. Materials for coating is mixed to the plasma jet from here, over here, and here. And plasma jet is brought out from this small hole and go to the target surface. And these low temperature plasma are very useful for many applications and not damage even if we irradiate to human skin. But if we would like to irradiate high density plasma, plasma gas temperature getting higher from the room temperature, because we need high power to generate high density plasma. So we designed and developed a temperature controllable plasma. In usual low temperature plasma is generated using room temperature plasma gas. But in our temperature controllable plasma, the gas temperature is controlled before the plasma generation. With this method, we can generate a below 0 degree plasma. If we irradiate minus 90 degree plasma to water, ice is generated here in just 10 seconds. We can control the plasma gas temperature independently to the discharge power or gas flow rate from minus 20 degrees and 40, 100, 120, and go down and go to room temperature. We can control the plasma gas temperature. Next, we developed a multi-gas and a temperature controllable plasma. This is the design of our temperature controllable multi-gas plasma jet. Plasma gas temperature is controlled by heat exchange with temperature control fluid in the wall of the plasma source. The heat exchange flow path is here. These are heat exchange paths, and these are very complex. So we made this plasma source using metallic 3D printer. In this case, we made the body by aluminum. And just the shiny part, this one, are created by usual machining. We can generate any kind of gas plasmas like this. 1 year ago, a compact model of this plasma source was press released from Tokyo Tech. And this is the latest model of the temperature controllable plasma. The plasma gas temperature is measured in real time using optical fiber, maybe this one. And the plasma temperature was feedback controlled. By this new device, the plasma gas temperature could be controlled with an accuracy of just 1.2 Kelvin. Okay, I will now talk about our research on applications using these atmospheric plasmas. The first target is sterilization of or virus inactivation. When plasma is irradiated or directly introduced to liquid by bubbling like this, a large amount of reactive species are introduced into the liquid. They produce various effects, such as sterilization or treatment of liquid or surface treatment in liquid. And this is the result of disinfection of bacteria in water. By oxygen and nitrogen plasma, general bacteria were sterilized by more than 5 orders in 1 minute treatment. But disinfection of spore-forming bacteria was not so easy. We need 3 minutes using oxygen plasma. But other plasma does not affect to the spore-forming bacteria. Next target is inactivation of viruses. There are 2 types of virus. They are enveloped and non-enveloped virus. Enveloped virus such as COVID-19 can be easily disinfection by alcohol, but non-enveloped virus cannot. These are result of virus inactivation by plasma. Both enveloped and non-enveloped were able to inactivate more than 4 orders in 60 seconds. By plasma, both type virus were inactivated without much difference. Next application is drug measurement. We have developed a method for analyzing drugs deposited on the surface using low temperature plasma. If plasma is irradiated to the surface, molecules on the surface are removed or dissolved by reactive species in the plasma. Dissolved molecules have charged by proton attached from ambient water vapor. Then they are introduced to a mass spectrometer. We measured medical tablet by using this method. This is an experimental setup. By using this system, some medical tablets were analyzed. We applied caffeine in estran mocha and etenzamido and isopropyl in Sarun. As you can see, these mass spectrums are very simple because the plasma temperature is low and the drug molecules do not fragment in the process. Therefore, we can easily identify the drug species. And it is very good point of this method. This detection limit was femtomole order. That is very good. The plasma is low temperature and touchable, so we can apply to human skin. We measured isopropyl antipyrine of 5 nanogram on a finger. 500 nanogram on a finger. As a result, we could measure it. In this case, some fragment noise like this was detected, but we could get strong peak, almost same with the case of plastic surface. Now we are using this method to analyze the composition of cosmetics and sweat on human skin. Our next target is inside the human body. This is our next challenge. To measure drugs in living body, we are developing the plasma injection probe. In this device, small plasma jet is placed in a needle. The plasma needle is inserted through the skin. The body is irradiated with the plasma, and drugs at the position dissolved and analyzed by mass spectrometer. The left picture shows a very thin, small plasma jet for the plasma injection probe. The diameter is 0.7 millimeter. And this plasma jet was installed in an injection needle. The right picture shows the plasma injection probe in biological stimulated samples. As shown in this figure, we can successfully analyze drugs in biological simulated samples. However, for practical use of this device, the analytical sensitivity must be improved, maybe 1 or 2 orders. Next, I'd like to talk about hemostatic application of plasma. As shown in this video, if we irradiate the plasma to the bleeding point, the blood is coagulated and bleeding will stop like this. In conventional surgery, various hemostatic methods can be used. However, there are limited hemostatic methods in endoscopic surgery because forceps mouth is very small. So in our group, a plasma hemostatic device and endoscopic surgery for endostatic surgery has been developed. The forceps mouth of the endoscope is about 3 millimeters. So we developed a small plasma jet and can be installed in the hole. This is a plasma jet for endoscopic hemostasis. The diameter is 2.8 millimeters. It would be expensive to make a small plasma jet device by machining. So we may use a metal 3D printer to make it. The cost is about $3. And this is a video of plasma irradiating to the bleeding spot on a pig stomach. The low temperature plasma does not give the thermal damage to the tissue, so the wound almost healed in just 1 day. Now we are currently developing multi-function endoscopic device to stop the even strong bleeding. In this device, in addition to the low temperature plasma, blood aspirating and electrocautery can be used. The last target in this talk is elemental analysis in single cell. It is not easy to analyze trace elements in a single cell. This is because there are no device that can analyze a single cell. Therefore, we have developed a droplet nebulizer. In this device, a small droplet injected by shrink of piezo actuator. By containing one cell in a droplet, single cell can be introduced to the high temperature atmospheric plasma. Just in case we used high temperature plasma. We applied this droplet nebulizer to ICP-MS. The cell is introduced to the high temperature plasma and ionized, then introduced to the mass spectrometer or optical spectrometer. This is an emission spectrum from a single plant cell. We were able to analyze elements up to sub-femtograms. Currently, we are analyze human cancer cells such as HeLa or iPS cell. In our group, high throughput single cell analysis system is being developed. Cells are injected through a flow cytometer. Those cells only target cells are introduced into the plasma using a diffraction plate of cell sorter. And many droplets injected from a flow cytometer, and we use a cell sorter and target cells, just target cells is introduced to the plasma. Now we are developing this metal cytometer US JSPS large grant. And if you have a good idea to use our atmospheric low temperature or high temperature plasma, please email to me. Or please visit our laboratory in Tokyo Tech and please touch the plasma. Thank you very much.
Thank you very much. Any questions from the audience?
Thank you very much. Have you tried to use the plasma to analyze the trace elements in soil? In soil.
Soil. It is not so difficult. We can use a solution. And the solution can be introduced to the plasma easily. So thank you very much.
I'm the shortcoming from JSPS Marco office. Thank you very much for your nice talk on the computation of low temperature corona plasma. I have a basic question. What kind of a principle are used to generate the low temperature plasma, and also what's the polarity of the plasma? And I think it is very difficult to carry plasma to long distance. So would you explain about that kind of basic things?
And this slide is showing the principle to generate the low temperature plasma. When we apply high voltage to the electrodes, discharge plasma will be quickly generated. In usual plasma, time scale to generate the plasma is order of 10, maybe 10 nanoseconds. But the gas temperature gradually goes up in milliseconds. If we apply a short pulse voltage, plasma is generated quickly, but the gas temperature cannot rise like this. So low temperature plasma can be generated by short pulse discharge. But as you said, the plasma reactive species easily back to usual molecules. So we made a supersonic plasma. I don't tell you in this talk, but very high speed gas flow. We use a very high speed, Mach 1.7 Mach speed. It can treat maybe 4 or 5 centimeters. So per materials treatment is not so easy by using atmospheric plasma, because atmospheric plasma easily touch the atmosphere here. So we need very, very high speed, but just for 5 centimeters. I'm sorry.
We have 2 questions from online. First one is that can atmospheric plasma eliminate fungus?
Yes, we tried some fungus can be eliminated. Yes.
Okay. Next question: what factors have to be considered when selecting types of gas for different applications?
We have not good answer, but we measured some reactive species in the plasma. In the plasma, in nitrogen plasma, OH radical can be made, many OH radicals is made in N2 and argon plasma. But very which plasma is good is not, we have not answer. We try at this time. I'm sorry.
Thank you very much. Thank you.
Thank you very much.
This speaker is Professor Yoshitaka Kitamoto. He belongs to School of Materials and Chemical Technology. His title is Biomedical Applications of Magnetic Nanoparticles.
Already. Okay, thank you very much. Thank you for arranging this event to all staff members, and also thank you for joining and for giving time for audience. So I'd like to share our study about the biomedical applications of by using magnetic nanoparticles. Our main theme is we like to use the magnetic field, the magnetic energy into biomedical field or biomedical devices. So the magnetic field has a lot of merits, the remotely controllable, and also we can put such energy into the deeper area in the body compared with light. So this is the typical example of the application by using magnetic technique. The first one is a very simple one. The magnetic materials can be attracted to the permanent magnet. This principle used for moving in particular the drug delivery systems. The second one is the sensing. The magnetic materials that we are using, magnetic nanoparticles, generate magnetic fields outside. By detecting this magnetic field by using magnetic sensor, we can know the place of the disease and also the biomolecular interaction with nanoparticles. This is used for diagnosis, such as the sensing or imaging. The third one is the heating capability of magnetic nanoparticles under the alternating magnetic fields. This heating is as a result of the energy loss of the magnetic materials under alternating magnetic fields. Probably you feel the hot AC adapters for PC or mobile phones. So that heat is caused by partly the magnetic devices in the AC adapters. That is the heat source of the magnetic materials. This technique uses such a heat as an energy loss for cancer therapy. That is called magnetic hyperthermia. But I introduced later this heat is used for drug release for drug delivery systems. So this is a typical example of the magnetic nanoparticles. These are nanoparticles, the TM image, roughly 10 nanometer or around 10 nanometer in size. This is the iron oxide nanoparticles. It is called the magnetite. But we use these nanoparticles indicate such nanoparticles are dispersed indicates the usually biomedical applications case in water or ionic water. So this is a typical example of the ferrofluid. The ferrofluid has a response to permanent magnet or magnetic fields. It's called the ferrofluid art. So we use usually these nanoparticles indicate for biomedical applications. So the first I'd like to introduce the drug delivery system by using magnetic nanoparticles. In this case, the delivery carrier are required to have loading capability and also efficient delivery to disease parts and also controlled release. I'm going to introduce the two kinds of magnetic nanostructures. This one is magnetic nanocapsules. This nanocapsule is composed of magnetic nanoshells around 10 nanometer in thickness. And the second one is magnetic composite, composed of the polymer and magnetic nanoparticles. In this case, the core is polymer. The polymer contains the drug, and the magnetic shell composed of magnetic nanoparticle assembly introduce a magnetic capability. So I like to introduce the magnetic shells. This is the synthesis scheme of magnetic nanocapsules. This magnetic capsule is composed of iron platinum as a magnetic materials. Usually in these applications, the iron oxide ferrite is used for biomedical field, but we like to use high energy magnetic materials in these applications. Usually magnetic materials, energy of magnetic materials depends on the size of magnetic materials, in particular nanostructures. In the case of magnetic nanoparticles, by reducing magnetic nanoparticle size, magnetic energy is decreasing. So if we like to achieve efficient delivery of magnetic nanoparticles and of the efficient applications, we need to control the magnetic energy to match the requirement. In this case, we like to synthesize the magnetic capsules with very thin shell, because to increase the loading capability in magnetic capsules, we need to reduce the size of shell thickness under the limited total size of drug delivery carriers. In this case, roughly the 10 nanometer in thickness. But in the case, if we use iron oxide nanoparticles to form these nanoshells, the magnetic energy is too low. That's why we use iron platinum as a magnetic shells. The iron platinum is studied now, the data storage materials. Usually the data storage materials is like a permanent magnet, such as a rare earth magnet. They have a large magnetic energy. That's why we use the iron platinum in this case. First, we prepared the silica particles as a template. Then we put polymer on the silica. Then we deposit iron platinum nanoparticles on polymer coated silica template. Then after this process, we have two processes. By dissolving the silica template, we have the composite magnetic shell composed of iron platinum nanoparticles and also polymer. This is very soft and also a little bit weak in structure, mechanical structure. After this step, we made the heat treatment in liquid under the high pressure and also high temperature. The iron platinum nanoparticles are diffused. Then after heat treatment, the network structure was obtained. This network structure was very strong in mechanically. Then after this explanation, I use this network structured iron platinum nanoshells as capsules. This is a typical example of the TM image after the deposition of iron platinum nanoparticles here. After dissolving silica template particles, a little bit different. This particle has roughly 300 nanometer in diameter. By using the transmission electron microscope, the electron beam cannot penetrate these large structures. But after removing silica particles, we can see the dot-like structures. This team image shows the magnetic composite of the polymer and iron platinum nanoparticles. And the second one is the nanostructured iron platinum capsules. You can see the relatively darker gray area and also the light green dark gray area. Dark gray area is porous. This network capsule has the porous structures. We can achieve the go into drug and also release the drug by using nanostructure. Then this is the SEM image after the cutting the nanoparticles. You can see the thin cell here. The size of these particles has 10 nanometer in size. The total size is around 300 nanometer, and the shell thickness is around the 10 nanometer in this case. By using this nanostructured nanoshell capsules, that we put the anti-cancer drug, that is called the doxorubicin. Doxorubicin has the fluorescent capability. This picture shows the iron platinum capsules are dispersed in water, but this iron platinum capsule contains doxorubicin in the capsule. Only the picture, the very black solutions. And after collecting these iron platinum capsules by using permanent magnet, you can see the supernatant here, and here is the attracted nanoparticles. We put these nanoparticles to cell A, and this water moved to the cell B. You can see the fluorescent image in A. In other words, the collected nanoparticle exists in cell A. Then this cell A shows the fluorescent. This means the nanoparticle contains the doxorubicin, which shows the fluorescent capability. This shows the proof of the attraction of magnetic capsules, including drug. Okay, this is another fluorescent image. This is the bright field image of cells. This shows the fluorescent image. This fluorescence is caused by the doxorubicin anti-cancer agent delivered by the iron platinum capsules. We can see the fluorescent image around the cells. This shows the cell contains the magnetic capsules with drug agent. This is the preliminary experimental results of drug delivery systems for only the delivery. Now we are moving to another applications. This is we are using these iron platinum nanocapsule for fuel cell catalyst. The iron platinum shows the catalytic capability. This nanostructure is suitable for the very thin catalytic layer in fuel cell. Actually, the other groups are doing this research, but the basic structure is all totally same. Okay, the next one shows the control release. This is not iron platinum capsules. We used the composite of magnetic nanoparticles and the polymer. This control release caused by the magnetic fields. I explained it in the initial part. The typical example of magnetic application is the heating. By applying alternating magnetic fields, magnetic nanoparticle can be heated as a result of energy loss. By using this heat, we achieve the control release. This is the principle of the control release by using heat. First, we prepare the iron oxide nanoparticles. Then we deposit thermally responsive polymer on nanoparticles. This thermally responsive polymer usually shows the hydrophilic nature under certain temperature, we use the hydroxyl propyl cellulose. In this case, the typical transition temperature is around 42, 43 degrees Celsius. Lower than 42 degrees Celsius, this polymer shows hydrophilic. In that temperature range, this polymer can contain water-soluble drug with, of course, water. But higher than 43 degrees Celsius, this polymer shows hydrophobic natures. In that case, the water or drug in this polymer can be squeezed out. Of course, the affinity problems. This is the typical principle of the thermally controllable drug release by using the thermally responsive polymer. And also, trigger of the heating is magnetic fields in this case. Of course, that's why we can control remotely the release of the drug. Okay, the first part is the drug delivery by using moving principle and also heating principle. The next part is the sensing by using magnetic nanoparticles. In the last part of the drug delivery, I explained the composite of magnetic nanoparticles and also polymer. In the next session, in the sensing part, I introduced the magnetic composite of nanoparticles and also polymer to be used the biomedical sensing. This is the typical principle of the sensings. Our final target is the analysis is in the blood and also saliva, the other biofluid. Those biofluids includes the biomolecules such as the nucleic acid, proteins as biomarkers. We put such biomarker solutions, the nanoparticles. These nanoparticles interact with the biomarkers. After the mixing of magnetic nanoparticles and biomolecular analytes, we apply alternating magnetic fields, then we obtain the magnetic signal from magnetic nanoparticles. This is the principle of this measurement. This is physical principle. Here is magnetic nanoparticle, but of course we need to put some molecules to introduce the interaction between magnetic nanoparticles and also biomolecules as biomarkers. Here's only nanoparticles, here's the nanoparticles and also the biomolecule here. By attaching the biomolecules, then we apply magnetic fields. The magnetic nanoparticle itself looks like a compass that is those magnets. By applying AC magnetic fields, nanoparticle can't rotate. Actually, in the equilibrium state, not the rotation, not the vibrations. This vibration, you can see the speed of rotation is different from this one and this one. The smaller particle can rotate very fast, but larger particle, larger composite of nanoparticles and biomolecules can rotate very slowly. This difference shows the existence of biomolecules and also the concentration of biomolecules. This is the physical principle of our magnetic sensing. This is another explanation about by using the equations. That larger particles, composites, and the small particles. When we apply alternating magnetic fields, such rotation or vibration appear. This tau is a relaxation time. Relaxation time means how fast nanoparticle can rotate. time shows the very slow rotation. Can rotate very fast. The inverse of this relaxation time is the relaxation frequency. By detecting relaxation frequency from the frequency spectra, that we can note the frequency, relaxation frequency. In the case of smaller particles, the relaxation frequency is high. The relaxation frequency appear around this peak. In the frequency spectra of magnetic signal shows such peak, then this peak shows the relaxation frequency. That by attaching bimolecules, the relaxation frequency decreased in this case. In other words, larger particles can rotate or vibrate slowly compared with smaller particles. By detecting the change of relaxation frequency, we can know the existence of biomolecules as a biomarker and also the concentration of biomolecules. That I'm going to show the preliminary experiments of this sensing. That we used the interaction between biotin and also streptavidin. This is a very famous interaction of proteins. That we put biotin onto magnetic nanoparticles. Then we mix the streptavidin into the biotin modified nanoparticles ferrofluid. That this is better to see. You can see the peak here. The red arrow shows the relaxation frequency. In the case of the no streptavidin case, this green one shows highest relaxation frequency. By increasing protein streptavidin, the relaxation frequency decrease this way. This is another figures to show these behaviors. By increasing the amount of streptavidin to mix these solutions, the peak frequency, this frequency shows the relaxation frequency. This relaxation frequency decrease this way. Depending on the concentration of this streptavidin, the proteins, the relaxation frequency change this way. That's why we can know, based on this technique, we can know the biomolecular concentrations. So what happens in these solutions? The decrease of relaxation frequency shows the nanoparticles or nanoparticle composite increase in size in solutions. Such behavior happen in the solutions. This is the illustration in the solutions. By increasing streptavidin, the nanoparticles are coagulated. And the increase of size by increasing the protein concentrations. We are doing this biosensing study by changing these molecules. By changing these molecules, we can detect nucleic acid and proteins or other biomolecules. We are synthesizing nanoparticles, and also we modify nanoparticles by changing the ligands. And also, we will detect such biomolecules. Actually, this is the exosome. Our target is detecting exosomes for membrane proteins. So, this shows the illustration. By changing the ligands, we can detect the nucleic acids and also the proteins. This is our basic studies in the chemical or biomolecular part. But we are doing also detecting technique as well. This is the simple magnetic detection systems by using simple coil. This is handmade by our students. And also, the biomolecular interaction with magnetic nanoparticles and biomolecules are not uniform in decay. So I introduced the clear peak frequency shift as a result of the interaction between magnetic nanoparticles and biomolecules. But it is difficult to see such clear peak shift in the practical applications because the biomarkers concentration is very low, and also the interaction between nanoparticles and the biomolecules are not uniform in decay. In that case, very small change in spectra, only such small change we can obtain. To analyze such small change, that we are using the machine learning to obtain the precise analysis of the biosensing technique. Okay, I introduced the biomedical applications by using magnetic nanoparticles. The typical example is the magnetically guided drug system first, and also magnetic sensing for diagnosis in the second part. And actually, we are not doing the magnetic hyperthermia, but this hyperthermia, there is heating as a result of magnetic fields, can be used for the controlled drug release in drug delivery systems. And also, we are synthesizing the magnetic nanoparticles, in particular the magnetic nanocomposite, the magnetic capsules, and also magnetic and the polymer nanocomposite. By synthesizing these nanoparticles, we are doing magnetic delivery system and also magnetic sensing. Okay, thank you very much.
Thank you very much. Any question?
So I have a big interest in also question. So which is topic you are now mentioned about the sensoring and also how to say a kind of medical treatment, but besides drug delivery, is there any possibility where so medical treatment can be, so this technology can be used for the medical treatment, for example, some, so the pills, consider these particles or computer necessities, so culture pills can be easily destroyed. So I guess such kind of application will be available in the future. And after that, I don't know much here, so may I have some comments or opinion?
Thank you. Thank you for your comment. And the typical feature of magnetic materials, nanoparticles, the attraction and also heating. So these two feature is very important for the therapy, I think. The magnetic heating to introduce some release or something. And also the sensing is also important. Where nanoparticles or drug exists in the body. That's why sensing in other words, the theranostics can be achieved by using these magnetic nanoparticles or some magnetic field technique, I think. Thank you very much.
Thank you so much for your interesting presentation. I'm working in the diagnostic laboratories, in Sarun hospital. And I only have a short comment because your system magnetic field that you're detecting, I think it is not a high throughput inspections. So when we carry out the testing in the clinical setting, we have to do it very fast. So we usually use the page. This content, this is well on the one page for the testings and make the results to detect the positive and negative by sample. So to make it in the real clinical setting, I suggest that it should be carried out in the high throughput sometimes in the future.
Okay, thank you very much. Yeah, the multi-feature is the collecting magnetic nanoparticles and also this dispersion. That is the important to increase the speed. But in the practical application, we need to more studies. According to your comments. Thank you.
Thank you.
Thank you again, Kitamoto. Thank you very much. Well, okay, so as for the closing remarks today, thank you very much for joining us. And audience in the site, please fill in the questionnaire, or you can access to the QR code afterward. Anyway, I hope all of you will submit a questionnaire. And should you wish to collaborate with us, please feel free to contact this address. And Tokyo Research Showcase is an annual event, and we are planning the next showcase for 2024. See you again. Thank you very much. And for the audience on the side, we are preparing some coffee and sweets. Those will be served in the foyer outside the room. So all the speakers will join. Please use this occasion as a place to talk with the speakers. Thank you very much. And we'd like to take a photo for all speakers.